And when one paper cites another paper, that becomes edge. So papers linked by citations, that is one particular type of social network. Now, in this type of social network, so yeah, let me first talk about types of social networks. So then you, in the same scientific community, you have another type of social network where you have authors of the node, and two authors are connected if they have co-authored a single paper. They have written a single paper together or multiple papers together. They have an edge between them. So that is in co-authorship graph. So this is generally we call it citation network. And this will be co-authorship. Then you have, if you go to e-commerce websites, you will have customers, you have products, and customers are buying various products. Right? And generally, this is a bipartite graph because only customers and products are linked. So this is some sort of e-commerce website. You will have this particular type of graph. Then you have the web graph, right? So that means you have various web pages that are the nodes, and when a web page links to another page by using anchors, you have some sort of citation going from one web page to another web page. A link is going on. In Facebook, you will have friendship network, and some other social networks, you will have this friendship network where you have different people as nodes, and if you're a friend with another person, you have an edge between them. And similarly, in Twitter, you have following networks. So you have follower of certain persons, and you have certain followers. So these are examples of social networks. Right? Some examples, but I think you can actually give much more examples of social networks. Right? So now when we see these networks, so we see the underlying data is all a graph. You have nodes and you have the edges between them. Now the question is, what kind of applications you are looking forward to? What kind of things you want to do with these different types of graphs or networks? So let's see. So suppose, let's say this citation network. Right? And CiteSeer was one of the very popular citation network. Now there are actually much more. So, and suppose your application is this. So you are giving a query like social computing, or it can be random walks, and you want to find out top K matches, top K papers that match this query. And that is an application and that you are trying to find out. Suppose in the co-authorship graph, you want to say that, okay, I know Christopher Manning, one of the, I think, the most famous author in natural language processing, who are the most likely co-authors of Manning. So that means people who are likely to co-author with him in the near future. Right. In Amazon, I want to know what are the top K book recommendations in general, or maybe with respect to a particular query. Given a query, top K websites, right? That's the most crucial application that anyway, I think all of us are dealing with. Given a query, find out top K websites. And then someone who is joining Facebook, or he's maybe the person is already there for some time, what are the top K friend recommendations? Right? And I think you are getting it every day. That who are the people whom you can connect with? You are getting it in Facebook, LinkedIn, and all the different social networks. Who are the possible people you can connect? Now, these are just some examples of things you can do. But we want to have a very elegant framework for doing these tasks. And what is that framework? And that is where random walks come very, very handy. And how do they do that? That is what we will see in this session. So what we would see, a very wide variety of real-world applications. So the questions I was showing you in the last slide, they were all actually real-world applications that we deal with, like on every time. So we have a particular network and we want to rank entities. We want to rank entities maybe independently or with respect to certain query. In both the cases, I have to handle this graph data and try to do some ranking on that. Now, what is a framework that would be very elegant for ranking entities in a graph? So this is what is our main highlight, that we want to rank entities in a graph. And that is the reason we need a particular mathematical framework. So what random walk gives, it gives me a very graph theoretic measure by which I can rank nodes, compare similarity between nodes. So given a node, I can find out what is the other similar node for them. And that is very interesting for applications like recommendations, where we have a particular node in my graph, I want to find out other similar nodes for them. So we can say, for example, two nodes are similar if there are a lot of short paths between them. But mathematically, how do we express that? So in general, random walks have been like there for quite a few years, and they have proven to be very, very simple but very powerful mathematical tool for extracting this particular information. Now, what is a random walk? What is a random walk? How do we actually start talking about the formulation of random walk? What happens? So name tells a lot. Name tells a lot. You have random walk. You are on a graph, so you are assuming some random walker who is going through a graph, going through different nodes via the edges between them, and that's how you can actually visualize things. So you have a graph, so that is the input. You have a graph, and you have a starting point. There is a node, and you are starting there. And in random walk, what you can do, you can select the node will have various neighbors. You can select one of the neighbors at random and move to that. Right? And you keep on doing this. And then you select a neighbor of this node and move to it and so on. You start with a node, select a neighbor at random. Fine, I went there. Then again, I will select a neighbor at random for that node and I will keep on doing. Okay. And this sequence of nodes that I generate by using this random walk, the sequence of nodes is called a random walk on the web. Fine. So what? So the question will be, so what? So you have a graph, you have some nodes, you can do this random walks on the graph. So what is interesting about it? So I can do this random walks. So yeah, what is interesting about it? What can I get out of this different random walks? And that is what we will see. What can I get out of it? So for that, let's have some simple notations. So you have a graph. So let's say there are n nodes. So there are n nodes. And the end node, so there will be an adjacency matrix. Right? I suppose all of you know that this is a matrix that denotes which two nodes are connected to each other. And this is, you're taking a directed setting. So this will be an n cross n matrix. And any particular entry, say I, j. So this Aij will denote whether the node I connects to node j. So that is, and in general for weighted graph, you can have a weight on that. So weight on edge from node I to node j. That is what you are storing in the adjacency matrix. And if you have an undirected graph, it will be symmetric. So you will have Aij same as Aj if it is a symmetric graph. So this is the adjacency matrix. Now, how do we convert an adjacency matrix into a transition matrix? So this is an adjacency matrix. Now I want to convert that to a transition matrix. What do I do? So in transition matrix, what will happen? From each node, I'll get a probability distribution of transiting to any other node. So I'll get a distribution, probability distribution. Right now I'm just getting the weights. But how do I convert this matrix into, say, probability distributions? So what do I need to do? The only thing I need to do, from each node I, say node 1, I'll have A1, 1 to A1n, right? So they are telling me the weights from node 1 to node 1, node 1 to node 2, and so on. If I want to convert them to a transition matrix, I'll have to normalize that such that this row adds up to 1. This row should sum up to 1. So I can do that simply by dividing each entity by sum over 1j, j is equal to 1 to 1. Dividing it by summation of all the values in this particular row. And then I will get a normalized value and this will be a probability distribution. So this is what we do to convert this adjacency matrix to transition matrix. So this matrix is row stochastic. That is another way of saying it. Row stochastic means that each row is a probability distribution. It will add up, the values in each row will add up to 1. So this is row stochastic. And Pij is the probability of stepping on node j from node I. Okay. So how do I get that? So this is simply Eij divided by summation over j Eij. This is the formula we discussed, because I will add up all the entities in a row and divide each value by that. And that will give you the probability of going from node I to node j. So this is the formulation for Pij. And yeah, if there are any questions at any point of time, just you can raise your hand. So you now know that you can be given a graph, you can convert, you can get the actual adjacency matrix, and you can convert that into a transition matrix. Now, fine. Now what we can do with the transition matrix? The transition matrix helps in that now, when you are standing at a particular node giving a random walk, you know what is the probability of going to this particular neighbor, because now you have the probability distributions of going from node I to node j. So you will actually be able to find out what is the probability of moving from node I to any node 1, 2, 3 up to n. So this value you are getting in Pij. So that's a very simple matrix. So 3 cross 3 matrix. So you have initially an adjacency matrix A. So where you have just the weights from node I to node j, and you are converting that to a transition matrix. And how you are doing that? In this row, all values add up to 1, so no need to divide directly. Again, all values add up to 1, no need to divide. Here, the values add up to 2, so you will divide each value by 2. So this becomes 1 by 2, 1 by 2, and so on. So this was the adjacency matrix, and from here you got the transition matrix. Now, once you have got the transition matrix, now you can start your random walk. So how will your random walk look like? So suppose, so this is just a visualization that you have a random walker and holds a map, like where do I go, and can only go to the connected nodes, right? Only the nodes should be connected and only the random walker can go. So now it is currently at this particular node. Now at t equal to 0. Now what is the node it can go to in the next step? In this case, what is the node it can go to? Does it have any option right now? It doesn't seem to have any option, right? So it is only connected to this particular neighbor and doesn't have any connection with any other node. So it can only go to this particular node. Fine. So no option, so it will go to this node at each particular. Again, it tries to move. It tries to move. It has to go to some other node. You will see that it has no option again, so it can only go to this particular neighbor, right? This is the only outgoing edge from this particular node. So fine, at equal to 3, 2, yeah, from here to here, it is now at this particular node. Now at t equal to 2, when it is here, now it gets an option that it can either visit this friend or it can visit this friend. It can go to any of these friends, right? And it has equal opportunity and equal probability of going there. So at t equal to 3, now that's where the probability creeps in. It says that, okay, the random walker can be either here or here, right? It can be in either of the two positions, right? So now, actually, if you think about the random walks, you can get two possible random walks up now. You can say, okay, I have a random walk starting from here, then I went here, here, and then I may come here, or I can do this. There are two possible random walks you can do. Fine, but yeah, you can keep on doing that. You can keep on going further. You are here or here. You can again continue going further. Good, sure, I'll do that. But yeah, I mean, is that is she a jobless person, nothing else to do? We keep on going from one node to another. So what are we doing here? So fine, what are we doing here? So we have a random walk who can go along the nodes, following the links, following the probabilities. But what does that give us? What does that give us? Right? So think about this random walker, infinite time, right? All the time in the world. It can keep on do this walk, like the way we are saying. It can keep on doing do this walk. Now, can you estimate? Can you estimate what is the node it will visit the most number of times, or maybe which node it will, or let's say I find what is the probability of this random walker being at a given node I. What will be that after a very, very long period of time? What is the probability of this being at a particular node I in the graph? That is what is very interesting. That is saying that if I start, like, think about yourself as a random walker and the web being this graph, right? All the websites, and how do you go from one website to another website? You have a link that takes you from one website to another website. You have this whole web, and you are a random walker. You are going from browsing from one web page to another web page. Now, what is the probability that you will visit a particular node, particular website after? I mean, what is the probability of you visiting a particular website? And which website you are most likely to visit if you keep on doing that? And that is what becomes very interesting now. Oh, yes, this is what I wanted to do. I wanted to rank entities in a graph. And that is what we will do by this method. So that means we need to find out if the random walker keeps on doing this for a long period of time, what kind of probability distribution does it induce over the nodes, right, with which it can visit. So let's go to the actual notations. So let's say XTI is the probability that the surfer is at node I at time t, right? Don't worry too much about the notations. You only have to remember two notations. One is I have n nodes in my graph, right? I have n nodes in my graph. So at any point of time, my random walker can be at any of the nodes, right? But if I find the probability of it being at all the nodes, it should add up to 1. Right? So that means at any point of time, I can define a probability distribution with which the random walker will be at any given node. So one thing I need is a probability distribution over the nodes. Right? This will give dimension n, and let us use a row vector for this. So row vector, this here I'm saying xti. That is, I'll just write xt. Xt is a probability distribution that will tell me it can be anything. So it will be 1 for particular node and 0 everywhere else. So that means at time t, so it has a probability of 1 of being in this node I and 0 for being anywhere else. So from this vector, you can find out xti by seeing the ith index of this vector. You can find out what is the probability of the server being at node I at time t. Now, what I will do next, I will say that, okay, this particular distribution, you can compute it every time. So you can start from, say, time 0, you can go to time 1, up to time t plus 1, and you can keep on doing that. You can keep on doing your random walk, one step at a time, and at every step you will have a probability distribution. So you will have x0, x1, x2, xt, xt plus 1, and so on. This is what you will see. But every time, what you should feel comfortable about, this will be a simple row vector. It will be a row stochastic vector. It will add up to 1. The values will add up to 1. This is just a probability distribution of the random walker being at any given node I. So this is how I'm denoting the probability of the surfer being at node I at time. Now, this is one notation. The second notation I need. Now, what is the probability with which random walker can move from node I to node j in the graph, right? And remember, we have already computed a transition matrix P. So we have converted the adjacency matrix to a transition matrix. So that is row stochastic in nature. So another notation I need is a transition matrix P. And that will be an n cross n matrix. And all of you know what is Pij? Pij is the probability of moving from node I to node j in this particular graph. Yes. Probability of moving from node I to node j. Good. Only two things, nothing else. Okay. Now, I found out what was the probability that the surfer will be at node t at time I. Right? It will be a single value because now I'm going at the part of node. Right? The distribution was a vector, but for a node it will be a single value, node I, a single value. Now suppose you have to compute this. What is the probability that the surfer is at node I at n time t plus 1? How will I compute that? This is what this quantity tells. This particular value denotes. Probability that surfer will be at node I at time t plus 1. How will I compute that? How can the surfer be at node I at time t plus 1? What is the precondition for it? What is the precondition for the surfer to be at node I at time t plus 1? The precondition is that at time t, it should be at some node j. It will be a some node j, right? And then there should be an edge from going from node j to I. And there should be an edge from j to I, right? So how do I know that? So what will the probability of coming to node I? So what is the probability with which the surfer was at node j at time t? How do we denote that? X T j. Yes, the probability the surfer was at node j at time t times probability of going from j to I. That will be P of ji. That's it. Now, have I missed something? Have I missed something? So what I have missed is that, fine, this is good, but this tells me if it was at node j, it can go from j to I. But it could have been an any node j prime, and it could still have an edge to go to I. Right? It could have been a j prime, it could have gone to I. It could have been at some k, it could have gone to I. So I need to sum over all the possible j's. Right? So I need to sum over all the possible j's, and that will give me the actual probability of the surfer being at node I at time t plus 1. So summation over all j, probability that it was at j at time t times probability of going from j to. And this is what gives me the probability at time t plus 1 for node I. Now, fine, this looks okay. Now, can I write this more elegantly? Because this I'm expressing it for each node separately. Can I write it more elegantly so that I can express it for all the nodes together? So I can actually start saying in terms of what is xt? What is this whole distribution? What is xt plus 1? Can I compute one distribution from another distribution directly? So how will I do that? So now if you look closely what you are doing, so you had this particular, so suppose this is your index I, right? And this is again your index I. So you're computing this xt plus 1I. And how are you doing that? You are looking at, so this is your xt, 1 to up to n, and then you have a transition matrix. So you are saying, okay, how will you get this particular value at xt plus 1I? You want to say, okay, what is this? This is xt1, probability that the surfer was at node 1 at time t, times, it will go from 1 to I. 1 to I will be what? So 1 to I will be here. 1 to I will be this P1I, P1I. So this is, suppose this is your ith column. So this is your value that you're looking at, P1I. So xt1 times P1I. Plus, then you go to xt2, P2I, and so on, xt sum j, xtj, pj. And you just add up those. Right? So you multiply xt1 times P1I plus xt2 times P2I, xtj times pji. So you're actually doing nothing but you're multiplying this particular row with this column, just doing a dot product, right? And that is giving the probability distribution at node I at t plus 1. Now suppose you want to compute that for all the nodes. What you need to do, how you will get it for all the nodes in a single shot, what equation can you use? You can say, okay, fine, I will just multiply my xt with p and I will get this whole distribution. So xt plus 1 is nothing but xt dot product with p, right? Dimensions match. This is a row vector, so this is 1 cross n. It's one row and columns. P is a transition matrix, n cross n, and you multiply them, you get 1 cross n. We should always do this dimension matching. So that means I have a simple formula for computing xt plus 1. xt plus 1 is nothing but xtp. That's all. I just do this multiplication that gives me the distribution at the next point of time. Right. And there are only two notations we worried about. Okay. So, good. So I can compute xt plus 1 as xt times p. But you see, this is like at some point of time, t and t plus 1. This has been going on for quite some time. So I can keep on applying this formula again and again. So I can say, okay, this is nothing but xt. How do we compute xt? That is xt minus 1 times p, and then you have a p. Right? That is nothing but xt minus 1 p square. And I can again compute xt minus 1 as xt minus 2 p cube and so on. If I go to time 0, that will be x0, and this will become e to the power. Yeah, yeah, maybe it will be t plus 1. Yes, it will be t plus 1. Should be t plus 1. T plus 1. Right. So this is how you can get that. Okay. So that means you started with some initial distribution, you kept on multiplying with p again and again and again, you can get this xt plus 1. Good. So now the question is, what if the surfer keeps on walking for a long time? I mean, when we say long, I mean it's infinite time, but actually it converges. So what happens if it continues going for a long time? What will happen? So you will keep on going from x0 to x1 to xt to xt plus 1 and so on and so forth. And at some point of time, what will start happening? It will converge to a distribution. That means that at some point of time, x of t will be like very close to x of t plus 1. And if you keep on going further, this will not change. This will not change further. And this is where we will say this is converged. Okay. So what will happen then? So you will get something called a stationary distribution. Okay. And what is that? When the surfer keeps walking for a long time, uh, and the distribution does not change anymore. That means at some point, capital T, if you again compute xt plus 1. So xt plus 1 is generally what? This is xt times t, right? But what you will find, this has come out to be very similar as xt, or exactly similar as xt. It is not changing further. Okay. So, and that is what you are looking for. That is what is the stationary distribution that you are looking for. And for graphs that are well behaved, this even does not depend on the star distribution. And we will see why it does not even depend on the star distribution. So now, what is the stationary distribution again? So at a given node, this stationary distribution tells what is the amount of time a random walker is spending on that particular node. So if you keep on walking for a long enough time, you will spend some time at every node. So what is the amount of time or relative time you are spending on a particular node? That is what this stationary distribution is telling. Now, how do we compute that? So you have written this particular form, xt plus 1 is nothing but xt times p. So at stationary distribution, what will happen? Stationary distribution, this value will be same as xt, right? And that immediately gives you an equation for solving this. So let's say there's a stationary distribution that you're calling it V0. V0 is a vector, 1 cross n, and you're calling, to compute that, you're using this equation. That is, it will not change after that particular step. So V0 is same as V0 capital. V0 is same as V0 capital. Wow. Now, does that remind you of something, this equation, V0 as V0P? This equation might remind of something. Okay. So this is just nothing but a left eigenvector. You can generally you compute, when you say eigenvector, you compute right eigenvector. In this case, it comes out to be a left eigenvector of the transition matrix. Okay, and that's all you need. So that means the station distribution is actually a left eigenvector of the transition matrix. That means it does not depend on what is your initial distribution with which you start. You just need to compute the left eigenvector of your transition matrix, and that will give you the station distribution of the random walk. Now,
so we have one question.
Yes.
Yes, so we have one question. What is the justification behind manipulation to arrive at transition matrix for performing random walk?
What is the justification for?
Behind manipulation to arrive at transition matrix for performing random walk.
Right, right. So you see, what are you doing in random walk? What are you doing in random walk? You are at a given node in time, and you need to move to some other node. And when you're moving, you have to keep track of your probabilities. Okay, which node I can move to with what probability? It's not that you can move to any node. And if you have a high probability of moving to some node, you will go there. So the question then comes, okay, fine. So how do I define the probabilities from one node to another node? How do I define that? So originally I had no adjacency matrix, but they were just weights. They had nothing to do with probabilities. So I can be a node that is connected to every node in the graph. So I basically had a weight of 1 to all of them. So then the question would be, okay, how do I move to this node? Right? So think about the random walker. Let's say this here, this one. And let's say there are 3 nodes, and I am just defining some bits. So this is weight 2, this is weight 3, and this is weight 10. Let's say these were the weights. So actually they are only 2. So let me remove. So there are two edges, one with weight of 2, another with weight of 3. So the question is, how would we move to any of the nodes? The simple weights do not give me much information, but if I convert them to probability, then I immediately do that. Okay, let me convert them to probability. 3 by 5, 3 by 5. Now I know I can go from this node to this node to the probability of 0.4, and this node to this node to the probability of 0.3. That is the thing that transition matrix gives me. That adjacency matrix does not. This is what is the justification. Does that answer your question, or do you have some follow-up question on that?
Yes, sir. I think we have.
Right. So yeah, I'll be happy to ask your questions. Because I do not know otherwise whether you are following me or you have certain problems with the formulation.
Yes, sir. So I think Arpana has some question.
Yeah.
Yeah. So yes, we can continue now.
Okay.
Next topic. Yes.
Now, what is the criteria for distribution. When does it happen? So it happens when the graph is well behaved. And what do we mean by graph being well behaved? It means that there's a path from every node to every other node. The graph is actually irreducible, right? It's a connected graph. It's a connected graph. So for example, if we have a graph like this on the left-hand side, you see that this is not reducible. There's a path from every node to every other node. You can start from any node and you can go to every other node. Right? You can move here. But what do you see the problem with this node? What is the problem with this node that you see? So once you reach this node, you cannot come out. You cannot come out. So you are stuck here. And you can actually, if you think closely, you can also reduce this graph to simply two nodes that you are going from here to here. And once you reach to this hyper graph, you never come back. You never come back. Okay. So the graph that you are dealing with should be irreducible. There should be a path from one node to another node. And that is very important. That is what we'll tell you later on. That will what motivate you a concept called teleportation. So teleportation is a very important concept in uh, random walks. It will actually help in motivating that concept. Why teleport is important. And it should be a periodic, that if you take the GCD of all cycle lengths, that should be 1, right? So for example, if you take this particular graph, so you have a cycle of length 3. And these are the only cycles. You have cycle of length 3, you can have a cycle of length 6, and so on. So the period of all the cycles is 3. Right? On the other hand, if you see this particular graph, by having a self loop, what it ensures is that you can have a cycle of length 3, but then you can have a cycle of length 4 and 5 and so on, because you can have a cycle where you go to this node, again you go to this node twice, and then you continue. So the GCD of the cycle will be 1, and that ensure this is aperiodic. So we prefer this sort of graphs, that is, they should not be fixed length cycles that are the periodicity is greater than 1, and we prefer graphs where that are connected. So these are two conditions. And actually, it's the formulation tells you that even if you start with a graph that does not follow these properties, you can do some tweaking. You can tweak that graph to ensure that it follows these properties. And this is what you will see. What are those tweaking that you can do? So now let's take example directly of PageRank. That PageRank in 1998 when it was uh, introduced, and how it actually leveraged this idea of random walks for doing ranking the web pages. So what is the basic intuition of PageRank? So you have all the web pages on the web network, and each web page is a node. And we say that a web page is important if other important pages point to it. Right? That's the idea. A page is important if important pages are pointing to it. So that is the crucial idea. Now, how do I write this idea into an equation? Right? And actually, if you will see, this is the equation. So the importance of a page vi, the importance of a page vi, is nothing but if the important pages are linking to this. That is summation over all j that are linking to I, dj divided by out degree of j. Right? This is the formulation. Now, I have explained to you the normal random walk formulation, that how do you formulate the equation of random walk. Now, can anyone connect that to this equation? The formulation that I talked about. The formulation I talked about was some stationary distribution. You will have V0 is V0P, right? So this is what we talked about. On xt plus 1 is xtp. Now, can someone try to connect this formulation with this equation? That the importance of node I in the web is summation over all nodes that link to I, their importance is divided by their out degrees. How is that happening? So as per my equation, what would be Vi? What would be Vi? Remember how we computed the probability of reaching I? So that was nothing but all the nodes J. If the surfer is at J times probability for going from J to I. Probability J to I. Right? This is how we wrote the equation. Now compare these two equations. Can you connect? What is probability of going from J to I? How are you computing that? Going from J to I. Transition matrix at row J, and you have to go to this I, J to I. How do you compute that? So originally what would happen, in your web graph, you will have a link or not, you will not link. There's no weight directly given in the web graph. So you have either a 1 or a 0. So the adjacency matrix will look like this. So from at row J, you will either connect to 1 or not connect. You say you connecting to 1, not connecting to 2, connecting to 3, 4, connecting to something. That is your adjacency matrix, right? Now, how do you convert that to a transition matrix? This is your adjacency matrix. Now, how do I convert that to a transition matrix? What will be this entity? 1 divided by summation over that row. Summation over that row. And what is the sum over that row called? In your actual graph measures, what is the sum over this row called? So what is each one denoting? Each one is denoting that the node J is linking to a particular node in the graph. Right? So if you add up all the ones, what will tell how many nodes J is connecting in the graph, which is nothing but the out degree of J, right? So this is nothing but, the probability is nothing but 1 divided by out degree of that J for the Jth row, right? That's all. That's all is this equation. That Vi is nothing but summation over Vj divided by out degree of J. And that is your formula for patient, computing patient. It's so simple. So now V is what will be the station distribution of this random walker. Yeah, I don't know. This is repeated twice. Yeah, this was the actual report where it came out. So how many zeros? This is $25 billion, $25 billion eigenvector, the linear algebra behind Google. And this was the equation that they worked with for their initial Google search. Yeah, this is an actual example that how the webs would look like. So you will have various pages and they are linking to each other by using anchor text. And in this particular node, what you are seeing is the relative page rank for the nodes. So now forget about the size and the numbers for a while. Intuitively, do you see that which node should have the highest page rank just by looking at the connections? So if I just look at the connections, I see that E is very well connected. Connected means, see what is page rank? The page rank is high if many important pages are linking to you, right? So that means you need to have in degrees. A lot of people should link to you. So E is getting from many people, right? Getting from F. So E should have a high page rank. But instead, what we see, B has the highest. It also makes sense, right? B is getting linked from roughly everyone. B is getting linked from everyone. So that is also from C. But surprisingly, C has a higher page rank than E, and that is something difficult to understand, right? So C has a very high page rank. So compare C and E. The page rank of C is very high, much higher than E. While only one page is linking to C, and so many pages are linking to E. Why does that happen? Why does that happen? There is a reason. The reason is that, yeah, the most important guy is referring me. So that means the most important page, that is B, is giving a link to C, one thing. And second, you remember what was VI? VI was summation over VJ divided by out. Interestingly, here J is not J is not giving link to many people, right? J is only giving link to C. I mean, B is only giving link to C, no one else. So that means the whole of this page rank directly goes to C. Directly goes to C. Right? So C becomes very rich just because the richest person has given a link to him and not to anyone else. If B would have distributed its link, C would not have got such a high page rank. So this is how you can see how the page ranks actually come on the web. And yeah, this actually also led to many problems that okay, people started creating fake web, because once they came to know this formula, you know that yeah, you can always try to fool the system. You can try to create a lot of pages. You can give link to each other. And you can do all sort of things. But yeah, there were remedies for remedies. For. So yeah, so this was the example of paging. Now the question that will come before us. Fine. See, we talked about this page rank formulation, roundabout formulation, but this was applicable only for well-behaved graphs, right? Well-behaved graphs means there were two things: irreducible and aperiodic. That means uh, there should be a path from one node to every other node, and there should not be cycles of fixed length. I mean, their GCD should not be one. So, how do I ensure that for a web graph? In web graph, it may always happen that there is a new node and that is nobody is linking to that. And once you go there, it has not linked to anyone, so you cannot come out. Right? It can always happen that you have a cluster. You can go to here, you can keep on going from here to there, but you may not come out, and there is a whole network outside. That is all right. So, but once you go here, there is no coming out. So this is always possible in a web network or any other network that is possible, or any other social network. So now that means it will not be a well-behaved graph. It will not be a well-behaved graph. So how do I actually handle the situation? So what do I do so that my formulation works for any such graph? That is where the idea of teleport comes in. So I can make certain little tool for handling the situation. What is that? I say that okay, at any point of time, for my random walker, it knows what are the nodes it has to go to. It has that probability distribution of going to other nodes. But there are many other nodes it is not going to. Right? So why can I ensure that this has a non-zero probability of going to every node in the graph? So I introduce something called teleportation. So I say, okay, so I say with probability C, you can go to any node. That means that C will be divided across all the nodes in the graph. And with 1 minus C, you can follow your original probability distribution. And that's all. So that means I can have a modified transition matrix where I had the initial transition matrix, I just multiply by 1 minus C, but to ensure that this remains a transition matrix, I have another C times U. Right? What is this U? What is this U? U is again a matrix, but this is a uniform matrix. That means each entry is nothing but 1 by n. UIJ is 1 by n for all ij. Okay. And just take a moment and you will see that now I have ensured everything. If Uij is 1 by n for all ij, that means I also have Uii as 1 by n. And that means I have a self loop. As soon as I have a self loop, this becomes the GCD of all cycles becomes 1. Right? So that problem is gone. And because I am anyway creating a very small probability for going from this node to every node, that means my graph becomes irreducible. I have a path from one node to every other node in the graph. So both of these are ensured by this just simple trick called teleport. So okay, so then what is your method for computing patient? Right, you have the graph, get the adjacency matrix, compute transition matrix, and apply teleport. And get this modified transition matrix by applying teleport. And once you have this, now call it your transition matrix, then how can you compute the stationary distribution? So you can of course solve for the eigenvector, but generally people don't do that because you can use the other thing that if I keep on multiplying my initial distribution with p, keep on doing that, at some point of time it will converge. So at some point of time, if I keep on multiplying my x0 with p, x0p, when I reach x0 pk, at some point of time I will reach my steady state, right? So that is what we can use. So you can use an iterative programming where you can compute this vector again and again, and you can compare the difference between the two. Once it is the distance between the two conjugative vectors is below a threshold, you can say, okay, I can stop. This random walk has converged. The distribution has converged. So let's take an example of an actual example of a toy web graph. So what you see here, so there are seven web pages, D0 to P7. And they are linking to each other with certain anchor text. Right? So suppose D0 is linking to D2 with car, D2 is linking to 0 with GM. Now this anchor text is not much important to us right now for computing patient, but they're just given to. Now you have to compute the page rank for this graph. What are the steps? You don't need anything else other than this graph, the picture that I'm showing you. What are the steps? The first step is I need to get the adjacency matrix A. Now this graph I can convert into an adjacency matrix very simply. So this will be a 7 cross 7 matrix. And now say D0. D0 goes to only D2. So this is D0, D0, D1, D2, and D0, D2 will be 1, and everything else should be 0. Similarly for D1, D1 only goes to itself, so D1 to D1 is 1, and D2, it goes to D0 and D2, so it will have D0, or it also goes to D3, and it goes to D2, it goes to D3. Yeah, and so on. You can fill that. Right? Now, once you have this adjacency matrix, next step you can compute a transition matrix. So you can, the first two rows I think you need the same. There is only 1, 1. Third row you need it 1 by 3, 1 by 3, 1 by 3. Everything else here. Okay. What is the next step? Once you get the transition matrix, the next step is so you get D1 had two outlets. Yes, to D1 and D2. So it was an extra 1 that should have gone to up. So yeah, so you compute this transition matrix. What is the next step? Someone like to, you can raise your hand. We will unmute you. What is the next step? Next step is I need to ensure that this matrix is well behaved. So I need to incorporate the teleport probability. So I need to incorporate teleport. So remember what we used to do in teleport? We would say fixed probability C is reserved for going to all the nodes with equal probability. And with 1 minus C, I will follow my original distribution. Now, what is the value of C that we take? So generally people take C very close to 0.15. So C is taken something like 0.15. In this case, because I have to divide it by 7, so it will be easier for me if I take C as 0.4. I can then divide by 7 and become 0.02, right? So I will take C as 0.14 and 1 minus C becomes 0.86. So if I do that, can you say what will be this corresponding row after I apply teleport? So after I apply teleport, with the probability 1.14, I can go to each node, and there are 7 nodes, so I will divide 0.14 by 7. So each node I can go to 0.02, 0.02. Forget to, I will talk about this later because it has some probability. 0.02, 0.02, 0.02, 0.02. Right? All the nodes, you can go with the probability of 0.02. Now, what happens to the node where you already have a probability earlier? You can still apply 0.02 there. Plus, with 1 minus, you have to follow the original probability. So, plus 0.86. So, the actual value will be 0.88 for this particular point. Right? And you can verify that if you will add this, this will be 1. And this is quite straightforward to also prove because you are multiplying with, you have the probability that is adding up to C, and you have another probability that is adding to 1 minus C. So if you add these two, you will get 1. So this row will add up to 1. All the rows will add up to 1. Suppose you take this particular row, what will happen? This will be 0.86 times 0.33 plus 0.02. This will be 0.02 and this will be, these three will be same. Right? And you can figure that out what will be this. So after you apply teleport, this is how your matrix looks like, and remember this is what we found out. This will be 0.88 and everything else will be 0.02. So you have this transition matrix with teleporting. Now what will you do? What is the next step? This is your p hat and you are good to go ahead with this. What is the next step? I need to compute the state distribution, right? I need to compute the x. And how do I compute that? Very simple. Start with any initial distribution. So my x is now the vector of 7 dimension. Yeah, there's a hand. Yes, you can unmute yourself, fine.
Sir, am I audible?
Yeah, I can hear.
Yeah. So for how many iterations we need to go for do this procedure again and again?
Yeah.
So what should be the convergence where we need to stop this?
Right. So what do you think? What should we do? So see, we start with any initial distribution. It can be like a uniform distribution. Let's say this is a uniform distribution. I keep on applying this matrix P again and again. What I will do, you would have seen in any iterative programming like Newton-Raphson or any other method. What you do, you find out the difference between the current distribution and next distribution. So, and you will take, say, L2 norm of that. And you will say, okay, if this is below a particular threshold, the threshold you can decide this can be something like very small value, 10 to the power minus 5, 10 to the minus 6. If it is changing with a very small value, this can actually depend on your initial distribution also. If this is below a particular threshold, you will say, okay, I will stop. Like in this case, for example, what happens? You start with this initial distribution, and when you multiply with this matrix, you will get some values. Okay, and you will see that initially there will be a lot of change. There will be a lot of change. But now you see the change has reduced. It's very little change that is happening. But there is still change. You continue, and you will see, okay, now after a certain point of time, yeah, even here there was a change. 0.2 3 to 0.31, no other change. But here there was no change. So once you find two successive uh, points where there is no change, maybe you can take, oh, there is no change after 2 decimals or after certain number of decimals, depending on your graph. Then you say, okay, I stop there. And this is where you say, okay, I have achieved my stationary distribution. And this will actually depend on your size of graph. If your graph is much larger, you will take much more iterations. If it is smaller, it can actually converge very, very fast. But yeah, generally it does not take too much. You can also put a criteria like, okay, we will not go beyond a particular number of iterations. So you can say, okay, I will not go beyond 20 or 30 iterations. And that much iterations are sufficient to come very close to the stationary distribution, even if it is not stationary. So yeah, so not many iterations are generally needed. And you can even find your stopping criteria by computing the difference between the successive vectors, probability vectors. Okay, so I hope that answers. So, and you can start with any initial distribution. It actually does not matter. You will finally converge to the same stationary distribution because of the property that this is nothing but the left eigenvector of your transition matrix. Okay, now, yeah, I will not show you, but now can you tell me, or you have already seen, but which node has the highest page rank? And even if you have seen, can you reason out which node has the highest page rank and why? What are the candidate nodes for having the highest page rank here? Anybody would like to just guess, try? It's okay to be wrong. So a page will have a high page rank if high page rank nodes link to that. So which node do you think here will have the highest page rank? So I see two candidates for this. One is D2. D2 has a lot of links. Another I'm seeing is D6. Right? D6 has a lot of links. Three. Which one will have a higher page rank among these two? They look very similar, some sort of. There's one thing, right? See, D2 gets a link from D1, but D1 is in itself very small because D1 just has a self loop, nothing else. And D2, when it goes out, there's no way to come back. I mean, apart from teleportation, there's no direct probability for coming back to D2. So once you go out of D2, there is no coming back very easily. There's a very small probability. But on the other hand, D6, you see, D5 is very similar to D1. D5 is very similar to D1. But once you go out D3, you can again come back to D4, and D4 you can go back to D6. So D3 is, there's some way to coming to this node D6 from D3, even if not directly. You can go from D6 to D4 and from D4 to D6. Right? So you can come back to that, even if you go out. And that means, and D3 was also quite influential in itself. So D3 again gives an indirect link to D6 via D4. So that is where, and compare that to D0. D0 had nothing else other than D2, but D4 has support of D3. So D6 looks much more promising to have the highest page rank. And of course, D3 and D2 should also be having high page rank, but D1 and D5 should have low page rank, right? And that's what you will see. So D6 has the highest, then D3, then D4. Or D4 has high, D2 has just 0.11, the fourth, and then you have the other things, D0, D1, and D5. They have a small page. So you see, this is how intuitively you can see how page ranks are actually being computed for the banks. Now, before uh, I'll not talk about various variants of this normal page rank. But before I do that, let me just talk about certain quick applications for page rank. So remember the slide I had shown you where I was talking about various networks, and you can actually rank entities on a network using the random walks. So you can actually apply this page rank over any particular network. But let's say even if I try to do it for a very different application, like you're given a piece of text, a document, and you want to find out a summary of this, a summary of a document. You can still think of applying page rank. Now, this is something one of our research got earlier. So what we did there, so summarization. So what is this? In the summarization, you have a document, and you have to find out important sentences that are contained in the summary of the document. So what you can do, you can think of document as consisting of sentences, S1 to S and N sentences. And now once you have this N things, you can immediately say, well, what can you do? You can think of each sentence as a node. So S1 becomes a node, S2 becomes a node, Sn becomes a node. Now you have a node, and then we say, okay, how will I connect? How will I connect two nodes? You say, okay, I will connect two nodes if the similarity between them is above a threshold. You can compute some threshold, say above 0.5. If similarity of Si, Sj is above 0.5, that means Eij is equal to 1. You connect an edge between them. So like that you will actually induce a network from on this document. So we have a network consisting of sentences and their connections. Now, once you have these connections, you have to find out the important sentences. So you will just, what you will do, you will actually run page rank. You will run page rank on this, and you find out sentences that are the most important. And that will be your output. So find out the important sentences. Important sentences, that is equivalent to sentences having high page rank values. And this is a very good summation algorithm that is unsupervised. You don't need any supervised data. You can just apply it on any document where you have a lot of sentences. You can have a lot of tweets out of on the corpus. You can just create a graph out of that and use this method to create a summary. And that's a very popular summary called Lexan. We had worked on some variation of that, but the original method is called Lexan. That is for summation. That is one. Similarly, one very important place where these random walks have been recently used is something called network embeddings. I don't know whether you have heard that term. This network embeddings will be covered, network representation will be covered for you in some future session. So what happens here? So you are given a particular network, you want to find out embeddings for each node. You want to find out embeddings for each node. And embeddings was nothing but some fixed dimension vector, a fixed dimension vector that captures some property like, okay, two nodes that are similar in some network property should have very similar embeddings. So that is the idea. Uh, to, to compute network embedding, some of the very early methods were node to web and deep fork. And what they used to do, they what they used to do, so they will actually apply a random walk on the graph. So they will take the graph and apply a random walk, and they will generate the random walks. So instead of generating the distribution, like remember in the summation what we were doing, we were generating a distribution. In this case, what they will do, they will generate the random walks. So they will have a sequence of nodes. So they will have a random walk of size 10. The size 10 random walks. And there you will have, say, a node N1, N50, N100. N1 is connected to N50, N50 is connected to N100, N100 connecting to N200, and so on. Okay. So you will have lots and lots of such walks. Now, once you have a walk like that, now they were applying a very standard method that is there in natural language processing. I don't know whether you know that, but this is called word word vectors. So what they do that, okay, I get the representation of a word by seeing what are the words that appears in different contexts. And they said, okay, now I can apply this random walk, and now I can think of these nodes as my words and apply that method. I won't go into detail and details unless someone has a question. This will take me some time in explaining. But idea is that once you have the random walk, you can go back, assume that, okay, now individual nodes are my words, apply this method, and this gives you a embedding for each node. And this was one of the very popular methods for network representation earlier. In, we have used that in one of our works that was in NACL 2018. We had tried to use that for computing word representation using distribution semantics of the Soros network. So I'll just quickly show you what is that. So this happens for the association network. No, I think I'll come back to it. I have to move to another device for this. So these are some very specific applications that we had worked on using this. I'll show some later on. So now, let me now talk about certain variants of this normal random walks. So till now, what we have seen, we are looking for a vector V that satisfies this particular equation. So V is V times 1 minus C capital P. P is my transition matrix plus CR. And this C is the teleport. And R was a uniform probability given to each page. So you have some uniform probability going to each page by using teleportation, and then you have the original transition matrix. And you were trying to solve that and getting your stationary distribution. Now this is the general Pearson. Now suppose I want to personalize that. Why do I need to personalize Pearson? Think about the web. Web has like documents from all over, and there some documents are in specific languages also, right? Now think about you being a user of India. You will very hardly go to websites that are in African and other languages. And if I know very specifically about yourself, I can even locate what are the web pages that you're never going to put. So what is the use that I should have a uniform probability of going to every node? There is no point of going to every node. So what you can do, instead of having a uniform probability, I can have a personalized probability. I can have a personalized probability. And because you as an individual will possibly visit certain pages much more than other people do. So I can, instead of giving a probability of 1 by n to each web page, I can give a high probability to certain pages and a very low probability to pages that you are completely unlikely to visit. Right? And this is, so if I do a uniform distribution, I get page rank, but if I do a non-uniform distribution, I get a personalized page rank. Okay, so this is how you can do personalization, and that can come by looking at your own distribution. I can look at what web pages you are generally going over a certain period of time, and based on that, I can create a personalized vector for you, and that can replace this R. And I apply the same random walk and this gives me personalization. Right? Very simple trick. The same formulation you can capture personalization. Similarly, so you will teleport only to a set of web pages instead of teleporting to all the pages. And this is a non-uniform preference vector that will be specific to a user. So it can be learned separately for each user. For each user, you can compute by using the cache of that user. And that will give you the personalized view. Similarly, I can talk about a topic sensitive paging. So idea is that suppose, so this comes from the efficiency perspective. So think about the web being divided across in various topics. So for example, there will be topics about sports, there will be topics about health, there will be topics about entertainment, politics, and so on and so forth. There will be topics, there will be various topics on the web. And suppose you can broadly divide into these key categories. Now, I can already find out the pages in each of the category and compute page rank specific to each category separately. I can say, okay, I can have a page rank for sports, page rank for sports. That means I will get a page rank value for each node that has been tagged for a sports category. Similarly, page rank for each node that is tagged with health category, for entertainment, for politics, and so on. Now, how will I do that? So I'll get a query. Suppose I get a query. Given a query, I want to rank the pages. One thing is fine, I will just use the page rank directly. I can use the page rank directly. Second option could be I find out the similarity of this query with respect to all the K broad categories. I compute page rank a priori. So already have computed all the page ranks for each page in each categories, and then take a linear combination. Right? So I can say, okay, query. I can think of query having a 16-dimension weight. So let me call it k dimension for k categories, k dimension weight. So that means the query has a very high uh, probability to be in sports, but very low in health and very low in entertainment and so on. Now, I have already ranked each page as per page rank in each category. So I know for each page what is the page rank as per sports, what is the page rank as per health, and so on. Now, what I will need to do simply, I take this weights and multiply with the page rank of a page in a particular category. And that is how I can rank my pages. And this will help me compute the rankings for each page. And this page rank for each page in different categories can be done offline. So for each category, I can compute the biased page rank by teleporting uniformly to the website that are under that category only, right? So that we saw in the personalized page rank. So as your personalized page rank for each category, I can compute those scores. And at query time, I'll come to the probability of query belonging to each of the classes, and then take just a linear combination of the biased page rank scores that were already computed offline. So this can save me a lot of time. At runtime, I just have to compute this and take a linear combination. That's all. I don't have to compute page rank at runtime. So this is something again was popular to, for search. So you do topic sensitive page. Now let me talk about another very interesting aspect from random walks. So till now we were seeing, okay, I have a network, I need to rank the entities, and I need a global ranking. So PageRank gives me a global ranking that of this network, what is the stationary distribution, or what is the probability with which I will stop at a particular node. Right? This is what we were computing. But suppose now my problem set get changed. So instead of finding out a global list of global ranking of node, a global probability for each node, I want to say something. I want to say, okay, what is the affinity of node B with respect to another node A? That means, okay, given a node A, I want to rank the nodes. Right? And you see the problem becomes different immediately. This becomes very similar to, say, recommendation problem. that I have a network in which I have a node. I want to find out, okay, which nodes I should recommend, which nodes are similar to this. Right? And this is where I can also use random walks. And how do I? So this is what I call estimate the importance of node B with respect to another node A in the graph. So goal is compute the importance of node B for node A. And uh, and how do we modify the random walk? It's actually very simple, but yeah, slightly non-intuitive. What we do, so we take the same random walker, but now it starts from node A. Right? It starts from node A, and it will again choose from the available edges. So A will have some neighbors, it will go. But one thing it will do, once it goes to certain nodes, it will have some fixed probability to come back to node A, right? That's important because earlier in our random walk, there was no probability to coming back to some start node. It did not even need to know where I started. It can just keep on following the transition matrix. Right? But here we do something different. We say, okay, so you have at A, you have some neighbors, N1, N2, N3. So you have some fixed probability of going there, fine. You go to these, but once I reach here, I have a fixed probability of getting back to my original position, right? So how it helps that a random walker actually explores a lot around it and does not like go beyond it too much. So it goes around A, comes back to A, again explores. So it explores the area around A very nicely. So that is what happens in this particular analysis. Okay. So it starts from A, choosing from the between the available edges, except that before he makes his choice, with probability C, he goes back to the start node, right? And this is called restart, as if you are restarting the walk again. Right? And these have a name called random walk with restarts. So you can, as if you can restart. So how do we compute this? So let us say UAB is the steady state probability that the random walker will find himself at node B. Now, how will you compute that? Okay, uh, I'll use the same formula. I use the same formula. So here, A is my P transition matrix. Suppose U is my stationary distribution. So I'm saying, okay, there are two things now. 1 minus C probability, I follow my transition matrix P. And with CR probability, I go back to the original node A. Okay. So with some probability, I go back to my original node. That is the only difference. So remember, if you compare this with the normal baseline, what happened? There you had a uniform probability to go into any nodes. But here you are replacing that, you are saying no. You have a probability of 1 to going to A, the start node, and a probability of 0 to going to every other node. And that's all. And that is itself sufficient for ensuring that you only explore your network around the node. So here the CR is what we call as the restart probability. And you can see what will happen if your CR is high, what will happen if your CR is high versus CR is low. If CR is high versus CR is low, how will it impact your final random walk? Anybody would like to comment? What will be the difference when CR is high versus low? If CR is high, what does that mean? I have gone to a neighbor, but there's a very high probability I should go back to my original thing. So it has a very low probability of further exploring the neighbor. Right? So that means the random walk I will get are going to be very, very short. They are going to be very, very short. But if my CR is actually small, that means I have a low probability of coming back to A, but a high probability of exploring the neighbors. So that means for low CR, I will explore my graph much further. Right? So CR controls how far the walk wanders from the seed node before it restarts and jumps back to S. And high value of CR will give me short and local random walk, and low values will allow me to go further. A good choice will depend on the diameter of the graph. That is, there was a formula in the original paper, but generally it's, if your diameter is around 6, you take CR as 0.4. If it is 19, you take 0.15. So if you have a large graph, then you take CR to be smaller so that you can do some acceleration. Otherwise, it will not allow you to do any acceleration. But you are doing the restart so that you can do a correlation discovery. Now, once you can do that, you can now go back to my original slide where I was asking all these questions. Who are the likely authors for Chris Manning? So now you can go to Chris Manning node, you can apply random walk with restarts, and you can actually find out what are the other possible people that Chris Manning will collaborate with. Okay. So we talked about a very simple formula, and we said we can do a lot of different tweaks to make it from normal page rank to personalized page rank, topic sensitive page rank. We can even do random walk with restart where we can compute correlation or recommendation from one node to another node. And that has lots and lots of applications. Now I have two options now. I can either spend some time talking about various applications, or I can go further and talk about something called supervised random walks. So I can even supervise them for doing link prediction recommendation. Or I can take questions. So whichever you would prefer, and any quick feedback would be helpful. What do you think should I use the next half an hour for? I can talk about supervised random walks. I can take some questions. I can also talk about some applications. Some things, for example, we did with random walk with restarts. Anybody has a question till now? Okay. Any suggestion on on this? Okay. Raise a hand. Allow me. Okay. Yes. Yes, Aparna, you can unmute.
Hello, am I audible, sir?
Yes, Aparna.
Sir, during the whole session, you were telling us the formula and expression regarding to traverse across the network so as to perform random walk. But I found it like with the help of the mathematical expressions, we were somehow we were choosing some of the other heuristics. Rather than being called it as random walks, we were calculating, we were trying to transit from one node to another with the help of some or the other expression. And that means we were trying to select some of the other heuristics. So what you have to say, sir, regarding this? I mean, why is it called random walks? Like we were calculating the transitions, right? With the help of transition matrix. So this part I could get it.
See, for a random walk, the only thing you need is that once you are at a node, in the graph, so you have a graph, you are at a particular node A, you should have some probability of going to some other nodes, and this probability should add up to 1. So you have some neighbors you can transit to, and the probability of going to all the neighbors, they should add up to 1. Summation of all these probabilities, outgoing edge probability should add up to 1. And once you have that, then you have a random. You can randomly choose one of the nodes as per the probability. Right? When you say randomly, you mean as per the probability. You will choose the nodes. You can sample a node as per the probability, you can go there, and you can continue the random walk. And this is all we have been doing throughout. What has been the difference? What we have changed in the various formulation is that how do you come up with that probability distribution? How do you come up with this transition matrix P? That is all we have changed. So we said initial formulation is very easy. You can just use the adjacency matrix and convert into transition matrix. And then we said, okay, but that does not ensure certain properties. So we said, okay, we'll add some teleportation. But you see, after teleportation also, the probability of this node going to any other node in the graph, this will add up to 1. So that property is being ensured. So this remains a random walk. This remains a random walk. Similarly, what did we do in personalized paging? We said, okay, you don't go uniformly to all the nodes. For a single person, you can only go to a set of nodes. You can teleport to a set of nodes. And that became personalization. But again, we ensured that this probability adds up to 1. So this remains a random walk. So this remains a random walk throughout. So the random walk is very simple idea that you have a node, you have a graph. Each node there's a probability distribution of going to the nodes, and you can keep on doing that as long as you want. So this is being ensured in all the formulations, starting from the very first page rank, then the personalized one, topic sensitive, random walk with restarts. This is ensured throughout. Just that the heuristics bring out the application perspective that no, I want to find out pages that are important to particular node A. So then I say, okay, then I should have some specific probability to come back to this node every time. Right? That's all we added. But finally, this matrix remains close to partition. So everything that we formalize still holds.
That means like while calculating, we do not know where the transition will occur. So the destinations are random. They'll be defined by the probability distribution.
Right. So see, this random walk is just for explaining. This is just for explaining. But finally, as I said, what matters is the stationary distribution. And for that, you don't have to. You don't have to compute random walks. So you can once you understand the framework, that then you know that I just need to solve this particular equation. That's all. You need to solve the equation. This will give you a stationary distribution, and that is all you need.
Sir, one added query, like as we also all know that these network graphs have an important role to play in designing recommendation algorithms, and because our area is recommendation system, my area is recommendation system. What you have to say regarding the performance of recommendation systems if they are designed through network graph? Will it be like efficient? Are the algorithms more efficient as compared to the other concept if we materialize for designing our recommendation system? If we design through graph, then what you have to say about the performance of the recommendation system?
See, right now you will see any recommendation system, if it doesn't use the graph, it will not perform well. Right? So they need to use a hybrid approach. They need to use the actual content. They usually use the content. So the actual, maybe the text or images that are there in the each node, the node properties. They need to use the edge properties. They need to use the network fully. They need to use the network fully. But the question I think you should have asked is what concept of network they should use. So can they just use this random walk with restart, or should they use something better, right? And these are questions, and actually there are lots and lots of methods that are coming up. So random walk with restarts was popular at some point of time. Right now, if you see recommendation problem, people generally are going to this network representation, mainly this graph convolution networks that are that were the topmost methods right now for applying for recommendation. But then these are generic methods. So if you just apply a graph convolution network on a graph, you can get to something, but you will find out this is already done. So now what is new that you will do there? That is where what is important is that you understand your problem a lot. What is the domain specific things you can bring in? So how do you blend in the node attributes along with the network attributes, and to make your recommendation problem better? What are the uh, new insights you can bring in? As such, as currently for recommendation, especially in places where you have a graph, the network properties are are a must. You will have to use that. Right?
Thank you.
Any other questions right now? Okay, so what I will do, I will just yeah.
So I request participants to ask queries, and if you have any questions, please ask sir. Otherwise, we can proceed towards winding up the session.
Sure. So
Yes.
I'll show an application at this time. I can talk about the supervised random walk. So or maybe I'll just say a few words about supervised random walks first. So this is just an idea that is starting from random walk with restarts. So what is link prediction? That suppose you have a network, at some time you are given a snapshot, and you need to find out what are the new edges that will come in the network at empty time. I know you have already a session that is in, I mean, some other day on link prediction, so I will not tell a lot about this. But the idea is that whenever you can think of link prediction, you can think, oh, I can use the random walk with restart sort of idea. But that has a limitation. That is a limitation. Limitation is that you see what you were using, you were only using the network connections, nothing else. You were saying, okay, if this node connects to this node, I have an edge, otherwise I don't have an edge. And then you are going further. But you're never using the node attributes. You're not seeing, okay, link prediction will be important, like whether this person has very similar interest as mine. Now, how do I capture that unless I go to the content? Unless I go to the content. So, but how do I put that into a random walk framework, which does not even consider uh, the node attributes? It only sees the connections. It only sees the adjacency matrix. So that is where the supervised random walks were very interesting. We have actually used that in some of our works. So what they came up with. so so link. Now problem is link recommendation or link prediction. That is, in a graph, I want to predict some links at some future time. So you see, there are various things. So for example, if I'm talking about Facebook network, where I want to find out whom should I become, or whom should this person be friends with, whom should this person be recommended for becoming friend with at some point of time. So you see, the very important things like they should have common interests, common characteristics that may not be directly captured by the network, right? Uh, they should be in the same social circle and should be close in the network. That is the network part that's coming in. So the question is, can we think of a method that combines the feature of the nodes, user profile, along with the interaction, the edges with the network structure? Now that's where the innovation comes. So you can say, okay, we have the random up with restart, but that is limiting because it does not use the node properties. But for my recommendation problem, I need to use the node properties. So how do I blend in the node properties? So that is where the idea came in that, okay, can I use the concept of random of the restart, but also involve the node attributes in some way? Then this supervised random box came in. So what was that? So, so you see this, see the term supervised random box. That means you are training your random box that, okay, where should you go, where should you not go? So that means the transition matrix is not a priori decided by your adjacency, but the transition from node I to node J is decided by, it's actually a learnable thing. So you can think of it as, oh, between I to J, I have a feature. This is a feature. I have some feature vectors. All of you would know about feature vectors. So you can have feature vectors saying, okay, I and J have the common, they have the same They share 5 common friends, yes or no. They both use this particular language. They both have gone to this particular location together. So like that, you can define certain features. Now, you can write lots and lots of features. These features can be node-centric, these can be edge-centric, and you can define a feature vector. And then you can say, okay, but I don't know which features are more important for my task. So you can say, okay, I need to learn a function that will work on these features and give me a value. And that value will become my transition, the adjacency, right? And that is where the interesting things come. So AI is not a priori known, but it is being learned, it is being supervised to model the actual feature interaction, such that from your past data, if two users actually connected with each other, their EIJ will be higher versus two users that were not connected to each other. Right? So learn to bias a page rank like random walk on the network so that it visits given nodes, the positive trending examples, more often than the others. Right? That's where the learning happens. So use node and edge features to learn edge strength. And so you will give some positive examples and negative examples, and you should have your feature function such that the positive examples are likely to be used more than the negative ones. Okay. So how will you do training? So you will have a source node S and see link prediction. How would you do training? You take a previous snapshot, you know a node S, you know at after a certain time what nodes it has linked with in future. So that becomes a positive example. Everything else becomes your negative example. So you can give some positive and negative examples, right? So you have a node S, you have some training examples to which it has created link in the future. The goal is you have to learn a function that assigns a strength, random of probability to each of them. So you can think of it as a classification task that the nodes to which SS created edges are positive examples, everything else is negative examples. And then a classifier that predicts where the node is going to create links. Okay. Yeah, I'm skipping certain thing. I'll directly. Uh, so, so what we are having a directed graph DE. We have a node S, some destination nodes, and there are some no link nodes. That means which it did not create a link. Now each edge has a feature vector that we described. That is like what they do they have similar age? Are they the same age group? Are they from the same hometown? And so on. And then they have some interaction attributes that time of edge creation, how many messages they have exchanged, how many common photos they have appeared together, and so on. They have this edge vector. Now you are learning this function, and this function will give you a unit, right? It can be a neural network, it can be an SVM, it can be anything. It can be a machine learning model that will take this feature vector's input and give you a score, AUV. Right. And once you have this AUV, you have the whole framework of random walk with restarts. So what you do once you have AUV, think of it as your adjacency matrix and run your random walk with restart, right? And then you can find out, you're going to know what node I will link to. And if you are anyway learning your feature vector such that you give a high probability node to nodes that you are linking with and low probability to node that you're not. That is that. So, so random walk with restart is again run from S, and you get the station distribution, and top ranked nodes will be predicted. And so what you did, the only interesting idea here was that the AIJ that we were talking about throughout can actually be learned by supervision. And that's where this supervised random walks came into picture. And they had, they were using features like this. The number of common friends, uh, how many times they have occurred together in photos. Anybody has taken initiation of giving someone a friend request, the age of the edge, and so on. So there were many, many different features. So like that. So in summary, what I would say is that random walks in general are very, very powerful mathematical tool for ranking entities, and they have been in some form or another. So earlier they in the very pure form, but like from 2016, 17, 18, there were a lot of heterogeneous information networks came, and that's where the meta path-based random walks became popular. And now it's all about doing graph neural networks and GCNs now that are what are popular. But random walks have been there. You can use that for any graph. You can use them for not only ranking entities, you can use them for link prediction and recommendation. And like these are the two main papers that are about this random walk with restarts. That was in KDD 2014, 2004, and the supervised random walks that came in Wisdom 2011. Two of the very important papers. And of course, if you want to know more about what's currently happening in this field, you should definitely look at these conferences. The latest, what are the new research happening in KDD and what is the new research happening in Wisdom right now. So that is something that will uh, help you find out the latest trends in this field. Now, if there are questions, I can take up. Otherwise, I can also show you one particular application we did with random walk with restarts. Yeah.
Sir, one of the question is, yeah. So one of the question is that to what extent does this random walk is associated with the core periphery structure? Means, is it necessary to have a core periphery structure for random walks to be applicable to any domain?
No, that is with something called hits. This hits algorithm that actually came later than after random walks. This was a variation of page rank. Their core periphery structure actually helps. But in the case of normal random walk, that is not very, very essential. This core periphery structure.
So does that mean that page rank algorithm, which is associated with hits algorithm, is also following this random walk? And
it's also follows random walk, but it has certain intuition. The intuition for hits is that okay, there are certain hubs, there are certain authorities, and the hubs will link to the authorities. So this sort of structure is there in hits, and very similar sort of framework applies to this. But yeah, framework is slightly different.
so yeah, sir, we have one more question. Which data sets of social networks are available with the node attributes for finding similarities?
I think nearly with all of them, you will have node attributes. So remember the very first slide I was showing different social networks. We take about citation networks. Nodes are the papers. You see, a lot of node attributes are available. You have the title, you have the abstract, you have the keywords, you have the author names, you have so many information. You have, yeah, you can actually compute a uh, uh, paper representation by using certain embedding method. So this comes with node attributes. You take anything else, uh, you take like tools, so the Twitter situation network where you have people as nodes and followers as a link. Each person has a lot of attributes, like how many times that person tweets, uh, what are his like bio in his or her bio, what are certain things that person is mentioning, what are the lists that person is keeping. So they always come with certain node information. I don't think there will be any social network without this uh, node information. Maybe there is, but yeah, generally I've seen all the networks, they have this node information. You can name any one, you can find out that there will be node information available.
And sir, one last question is that how do we map the random walks with the GNN and GPNs, like with deep learning uh, for future applications?
Right. So yeah, GN and GCs are a very different sort of frameworks. Of course, they have some way because they are computing this. They are computing the representation again and again by using adjacency matrix. Some way they resemble, but they are very different sort of network where you are actually learning all your parameters. So in random walks, there was no learning that was happening. Given your original network, you know what is your final um, what is your final page rank and everything is no. There's no extra learning that you need to do. But on the other hand, in GCNs and GNN, all these neural networks, they associate a lot of different parameters that they learn. And this is what, if you have a large graph, this is what actually helps. If you have actually a small graph, if you don't have any supervised data, you will go back to this random one. Suppose I have, for example, I will just tell you, I have a few documents, I want to create a summary. I don't have any label data. I'll apply this space and calculate. But suppose on the other hand, if I have a lot of labeled data, I have a lot of even unlabeled data, I can make a nice objective and learn my GNNs and uh, learn the parameters and apply those. So those are recent deep learning based methods that all thrive on the data. But in random walk, you don't need that much data. You can apply on any given network, any given network.
Yeah, thank you, sir. Thank you for highlighting these queries and enlightening us on this important topic of random walk. And we have one more question for applications of page rank. What could be the possible applications of page rank
Right.
which we can
So
do in the future?
what does PageRank do? It ranks entities in a graph. Right? So PageRank, it ranks entities in a graph. Just see that. And this is a huge application. Right? Take any graph now. Web pages. It helped in ranking the web pages, which web page has the highest page. Now let's take something else. Your you can take your citation network. You can find out which paper has the highest page rank, which paper is the most crucial one. And you see, people used to use page rank for re-ranking. So suppose you have an entire network paper citation network, you can compute page rank. Now, given a query, you can find out top results based on certain similarity, textual similarity. But now you have to re-rank based on which one is most important. You can go back to their page rank scores and do a re-ranking. So you can use page rank for re-ranking an initial list. So you have an initial list of outputs, you can re-rank that based on page rank. You can combine this with the original list. And this particular application is applicable in any social network. I gave you one particular example that is like very different is summarization. You can use page rank for text summarization. You can think of different sentences as nodes. You can find out the similarity between them, think of them as edges, and then you can run page rank, and this will give you what is the probability of which sentence is the most important in the graph. That is one example. You can similarly find out which word is the most important in a document if you connect them by how much they correlate and so on. So like the page rank has lots and lots of applications. You can take any social network and you will find an application of page rank like very quickly. You don't have to think a lot because this is the go-to application, ranks entities in a graph. Anywhere you need that, you can apply this.
Yeah, thank you so much, sir. Are there any other queries?
as there are no queries. So thank you, sir. That was very spellbound and empowering session. This will help our listeners understand the topic in a very organized way. Before moving forward, I would like to inform everyone that feedback forms are available and we would be delighted to get your feedback with respect to the ongoings of the program here. To sum up the present session, we look back on the gist of it. We acknowledge ourselves with social networks. Here, the underlying data has a natural graph. We are most looking for ranked nodes for a particular query in social networks. The reason to choose it is for its wide variety of interesting real world applications that can be framed as ranking entities in a graph. Random walk is basically a graph with a starting point where we select a neighbor of it at random and move of this neighbor. Then we learned about probability distribution and stationary distributions. It has been a pleasure to host all the members and audience of the meeting. I am thankful to all the participants for joining us and attending the program. I take this opportunity to thank the entire committee as well as the audience for coming along with us and giving us their valuable views and time. I would also like to share my sincere thanks to the honored guests for sharing us with some of the finest management practices. All the participants of this meeting are inspired by your wisdom. Thank you everyone for your time and participation. Thank you once again, our honored guest. With this, we come to an end of the session for today. We await your presence tomorrow for the next session at about 9:30 a.m. Thank you.
Inside.
Thank you everyone. On the behalf of the entire team of MIT University Rajasthan, I would like to thank you for joining us here today. Now we may wind up with the session and sessions for today. Uh, Let us continue this sessions tomorrow with the same energy and enthusiasm at 9:15 a.m. Positively by tomorrow, 9:15 a.m. Please be there with us. Thank you. Thank you for staying tuned.